In this tutorial, we will be discussing the solubility of gases. You may remember that the solute solubility is dependent on the temperature and the pressure. The solute solubility is dependent on the temperature of a solvent, so as for solids especially, as the temperature increases, the solubility typically increases. The solubility of most solids increases as the temperature increases when delta H of the solution, the enthalpy of the solution, is endothermic. For example, more solute can be dissolved in a given amount of solvent in making candy. So sugar is more soluble in warm solvents. Gas is not only dependent on temperature, it's actually inversely dependent on temperature, and it's also dependent on pressure. For all gases, their solubility will decrease as the temperature increases. So it's opposite than a solid. For instance, the less solute retains in solution when the warm soda pop fizzes more than a cold soda. So if you leave a soda pop in a warm car, more of the gas is going to try to escape. CO2 is less soluble in warm solvents. The delta H of solution, the enthalpy of solution, is exothermic with gases because there is no need to overcome the solute-solute attractions of the gas particles. The larger the partial pressure of the gas is in contact with the liquid, the more soluble the gas is in the liquid. This is Henry's law. So right now we have it in equilibrium on the far left-hand side, meaning that just as many gas particles are escaping as there are entering. Think of this as a pop can. However, if you push the plunger down and you're creating a greater pressure in here because there's more collisions on the can wall, you're forcing more of those solute particles into it, more of those gas particles into the solution. There you still have some escaping, but more going in than are escaping. And then once again, it's going to reach the point of equilibrium where the amount escaping is going to equal the amount going in. Henry's law is the solubility of the gas concentration is equal to some constant which is different for every solute times the pressure of just the gas. So the solute S of the gas is the concentration of the gas in molarity. Kh is called the Henry's law constant, and it's unique for every solute. The solubility of a gas, S of the gas, is directly proportional to the partial pressure of that gas. So as the pressure goes up, the solubility will go up. As the pressure goes down, the solubility will go down. Let's put this into practice. If 2.64 grams of CO2 dissolves in 500 milliliters of water at 25 degrees Celsius, what is the Kh, which is the Henry's law constant, for CO2? The total pressure of the entire system is 3,340 millimeters of mercury, and the air pressure is 680 torr. Remember that torr and millimeters of mercury are the same thing. So that's the same thing as saying 680 millimeters of mercury. So why is the atmospheric pressure and the vapor pressure given to you? Because you need just the pressure of just the gas. So we need to subtract the air pressure out of the total to figure out just the gas. So let's go ahead and do that. Our total is 3,340 millimeters of mercury. We're looking for the pressure of the gas, the P of the gas, and we have the air pressure, which is the same thing as millimeters of mercury. So we're going to subtract that out, and that comes out to be 2,660 millimeters of mercury. We need to convert this over to atmospheres. So, the P of the gas is equal to 2,660 millimeters of mercury over 1. 760 is on the bottom. 1 ATM is on the top. Divide that out, it comes out to be 3.50 ATM atmospheres. Alright, so we need the solubility. S of the gas is the same thing as the molarity. So that means we need moles over liters. So we need to convert the 2.64 to moles, and we need to convert the 500 milliliters to liters. So 2.64 grams of CO2 over 1. The molar mass of CO2 is 44.0. We find that out by looking on the periodic table. There is 1 carbon and 2 oxygens. Carbon is 12.01, oxygen is 16.0. You add 16 plus 12 is 44. That comes out to be 0.0600 moles of CO2. We need the liters on the bottom as well, so 500 milliliters divided by 1,000 to get to liters. That comes out to be 0.5 liters. So 0.06 divided by 0.5. That comes out to be 0.12 molar. Now to figure out KH, remember our initial equation is S of the gas is equal to K of KH times the pressure of the gas. So we can plug them into this equation now. So 0.12 molar is equal to KH times the pressure, which is 3.50 ATM. Divide both sides by 3.50. Cancel, and your KH comes out to be 0.034 molar per ATM. And that's how you solve for Henry's law.